I want to introduce tonight's speaker, Jesse Johnson. Jesse, if you checked out his very impressive bio on the Data Mining website, works at Google as a software engineer and was formerly in academia and was a maths professor there. So please welcome Jesse.
Where should I hold this? Is this good? Thanks. Thank you all for coming. This is going to be interesting between coordinating the mic and trying not to fall off the stage. So there you can see all the slides. All right. So I'm going to talk about geometry and topology, which is a field that's closely related to geometry, which I'll talk about later, and data. So when you think about data analysis, data science, data mining, machine learning, you probably think about computer science, statistics, maybe a few other fields as where the ideas come from. But it turns out that behind all of these ideas kind of is a lot of geometry. And so in this talk, I'm going to try to convince you. In this talk, I'm going to try to convince you that this geometry behind the scenes is actually really useful and important in two different ways. So one way is when you're first trying to learn the field, so as a way of kind of introducing what's going on. It's a great way to build intuition about these algorithms and ideas without actually having to go into the nitty-gritty details of algorithms and equations and things like that. And then in the second half of the talk, or the second portion of the talk, if I have time, I'll try to explain how this can also be useful for coming up with new ideas for new algorithms, new techniques, things like that, based on more kind of cutting-edge, more abstract mathematics. In particular, this field called topology, which I'll tell you a little bit about. So we'll start with something very simple, which most of you have probably seen before. So we're going to take some data. So we're going to pretend that this is data taken from a forest where we walk around, and whenever we see a tree stump, we count the number of rings to see what the age of the tree is, and then we also, with the tape measure, we measure the width. I don't know what units those are in. I don't think the units make sense. That's not important. The point is that we've pretended we've plotted the data. So here we have the width plotted against age, and of course trees get wider as they get older, right? Because it gets a new ring every year, and so the data kind of trends up and to the right. And so when you look at these points, right, your eyes are, or I guess the part of your brain that processes images probably picked out a shape, right? You kind of see a blob, or maybe you see a line, and so that line that you picked out, or that you might envision there, is what you get from an algorithm called regression. Okay, so already we've got geometry there, right? Points and lines, except, well, there's something funny because the line doesn't go through any of the points, so we're going to not worry about that for a second. So we've got very basic geometry, very basic statistics, but what's interesting is actually not just the fact that that's a line there, but how we picked out that line. So if you took a statistics course, you may have heard things like least squares, or maybe gradient descent, even depending on who your teacher was. So we can certainly go into all the details, all the numbers about that, but the goal is to avoid that and keep it very intuitive. So in order to understand how the computer would pick out that line, what we have to do is think about exactly what that line means. And so it turns out that this is not just any old line. This is actually a mathematical model. I know I was always intimidated by mathematical models until I learned what they were. I don't know if you guys maybe you haven't heard that term enough to be intimidated by it. But so a mathematical model is just a mathematical construct that allows you to make predictions, right? So the question is, how does that line allow us to make predictions? And again, many of you have probably seen this before. But so if we found a new tree in the forest, right, that hadn't been cut down, so we can't count its rings, we could measure its width, and then we find where its width is on the x-axis. We go up until we hit the line, and then we go across, and we get an age. And so this model is going to predict that that's the age of the tree, right? And it's not going to be 100% accurate. In fact, based on this data, it probably won't be very accurate at all, but it'll at least give us a rough number. Okay, so the idea is this is giving us some more clues about where this line should come from. So and basically what we're saying when we do this is that tree, if we did know its age and we were to plot where it is on this picture, it would probably be right there, right on that line. there's a good chance it could be on that line. So in other words, what that line is telling us is somehow the most likely or the average age of all the trees with that width, right? And we're getting that even though we haven't actually looked at any trees that have that width yet. So in other words, that line is somehow telling us not just about the data points that we started with, but about all the data points that we might get if we knew everything about every tree in the forest, right? So I want you to imagine that we actually did know the ages of all the trees in the forest and we could plot them, right? So we plot all those points, maybe a few hundred points, and of course the screen turns black because those are big points and they take up a lot of space. So we shrink down the points. We plot a few hundred smaller points, and then let's go even bigger. We'll take all the maybe these are pine trees just to keep it consistent. We plot all the pine trees in New England. We have to make the dots smaller again, but we get this. So we're getting now probably millions. I don't know how many trees there are in New England. Probably millions of points. So we have to make it really small. And we do all the trees in the U.S., North America, the world, always making the points smaller and more, kind of more dense. And at some point, we don't see individual points anymore. Can you guys picture this? Are you kind of envisioning this? So instead of seeing individual points, we now see just kind of a cloud, right? A gradient. In some places where the points are closer together, we're going to see really dark. And in some points where there aren't as many, we're going to see light, right? And so if we've done this right, if we pick this line correctly, this line should be going through the place where that gradient, where that cloud is darkest. So the idea is that this line isn't just a line, it's actually this gradient, which is called, again, if you take in statistics, you may know this already, that this is called the probability distribution. And so the idea of the probability distribution, or it's the density function for a probability distribution, and the idea is that the darker a point is, the more likely a tree is a point representing a tree is at that point. So here are two potential probability distributions, and so somehow so again the darkness represents the probability that a randomly chosen tree will be at that point. So if we wanted to look at these two distributions and decide which one is more likely, well, I guess I was going to make you guess, but I'm going to put it on there. So why is the one on the left good and the one on the right bad? Well, so this should be darker where there are more trees, right? And so this one, the trees that we have in our data set are mostly in the dark distribution, in the dark part of the distribution on the left, and they're not so much in the dark part of the distribution on the right. In fact, most of them are in the lighter parts. And so clearly that one on the left is more likely to have generated this data set than the distribution on the right. So the way regression works, at least the way the theory behind regression works, is that we decide what our distribution should look like in general. In this case, it's going to be concentrated along a line and then get lighter as we move apart. And if you were to sort of take a cross section, you would see a bell curve, a Gaussian. Not really, because this is just a picture, but in theory, you that. And so then what we do is we take that distribution and we put it on we put it onto a piece of plastic, like overhead projectors, right, where you put the plastic down, and we slide it around over the data points until we find the position of this distribution where the points are in the darkest part of the distribution. In particular, if you were to multiply all the probabilities together, you would get the highest possible value, right? Because the probability of one point being someplace is just that probability. The probability of 2 points is the product of the two of them. And anyways, so the idea is we take our sort of model for what we think the distribution should look like, and we move it around until we find where the points are the darkest, and then that's what we decide is our distribution. And then of course we replace the distribution itself with just that line, which is enough to describe it. And so this is not actually the way the regression algorithm works. It actually uses some tricks to get past that. But the way the algorithm was designed was to basically give you the same thing as you would have gotten by doing this sort of moving, trying to get the darkest region. Okay, so that's regression. That's the sort of geometric perspective on regression. And so what we see in general, kind of what you take away from this, is that a lot of the I guess I'm just going to call it data analysis, since that doesn't have any political connotations. So in data analysis, often what you're trying to do is, given a data set, try to infer a probability distribution from it. And so in general, in practice, you never actually write down what that distribution is, or often you don't write down what the distribution is, but somehow that distribution is sitting behind the scenes. You're sort of, it's sitting back there giving you the output that you actually do want. Okay, so this is sort of regression or modeling. There's a few other problems in data analysis that also that you can also define in the same way. So here's the classification problem. So we have two sets of points, some of which are green and some of which are blue. And the question is, if I give you a new data point, should it be green or should it be blue? And so here the distribution, the model that we get isn't just on or off, it's green or blue. And really this should be kind of fuzzy, the line between them, but that's harder to draw, so I didn't do that. But anyway, so again, we have this geometric picture of our problem. And then finally, there's the clustering problem, which so these are the problems that I like the most. So there are obviously other ones, but so here, given some data points, we actually want to pick what the two classes are. So in this case, we start off with all the points unlabeled; they're all black, and then we decide that some of them should be blue and some of them should be green. And of course, we also could have split it up even more, since that green blob actually looks like maybe that's two different distributions, right? And so somehow it's the geometric structure that's telling us how to divide them up. Okay, so the point of all this is that at least these are geometric problems, at least in some sense of the term. Now the problem, of course, is that all those pictures I showed you were two-dimensional, and two-dimensional data is not that interesting, right? You never see two-dimensional data in practice. So let's get a little more sophisticated and talk about three-dimensional data, right? So now trees, well, in fact, all plants grow faster if there's higher levels of phosphorus. So I hear. So we'll now measure the phosphorus level in different parts of the forest, and use that, add that to our model. So we can do the same thing now with, I guess, two-dimensional regression, or three-dimensional regression, depending on how you count. So now we plot our data points. These are now three-dimensional data points, right? They have an x and a y in the horizontal plane, and then the z value, which will be the age. And so similarly, we can find a plane that gets as close as possible to all those three-dimensional points. And what that plane is telling us is, well, there's now this three-dimensional probability distribution, this cloud in three-dimensional space that's denser in some places and lighter in others. Again, this is supposed to be what would happen if we took all of the points coming from all the trees in the world and made them really small, too small to see. We get this cloud, and then this plane would be going through the middle of the cloud. So that's our distribution. That's our model, our mathematical model. And of course, we can make predictions based on this. Right? We've given a new tree with its phosphorus level and its width. We find a point in the horizontal plane that corresponds to that phosphorus level and width, and then we go up until we hit the two-dimensional plane, and that's at some height, which is our predicted age. Right? So it's all kind of analogous. Hopefully you guys see that that's analogous. Same process in just one more dimension. Right? So now with your three-dimensional data, of course, we never see three-dimensional data either in practice. So we're going to have to get more complicated. Let's add one more value, nitrogen, which I think also affects age. But now we've run into a problem, right? Because there's no such thing as four-dimensional anything, right? We live in three dimensions. So now we've left the realm of geometry. Now I know what you're thinking. There's time, and so certainly we could visualize this using time, but that gets a little funny just because now we've left all the dimensions are not all equivalent now, so we don't really want to do anything with time. So great. So our intuition stops here, right? We can't picture four-dimensional data. Some people may claim to. I don't believe them. We live in three dimensions. We're wired to live in three dimensions. But here's the thing about mathematics is that mathematics doesn't actually care what dimension you're in. The same things that we did in 2 and 3 dimensions, you can define all of that in four-dimensional space as well. And so these processes that worked earlier, the algorithms, the equations, they all work for four-dimensional data as well. And again, so even though in high school we don't learn about four-dimensional geometry, but actually mathematicians have been studying higher dimensional geometry for it even higher than that for hundreds of years in one form or another. And so we can still, so it turns out we can talk about geometry. And we can even, if you're willing to kind of indulge in some suspension of disbelief, you can even think about 4 dimensions, get some intuition for it. And so here's how I like to think about 4-dimensional geometry. So we live in 3-dimensional space, right? And so when we drew our 3-dimensional regression model, you could think about it as you have your 2-dimensional desktop in front of you, and then we have this 3rd dimension that sticks out of the desk, right? So all we're doing when we go from 2 dimensions to 3 dimensions is we're taking the points in the 2-dimensional plane and we're pulling them up into the 3rd dimension. Okay? And in fact, we could go the other way. We could, if we took, if we had a light that we shine down on the data points, we could project them. That's called the technical term is projection back into 2-dimensional space. So imagine if there was some kind of being, some kind of mythological being that actually lived in 4-dimensional space, right? I mean, again, you can't picture it, but you can believe maybe something. Well, I guess it probably doesn't exist, but we can at least imagine it, right? And so this 4-dimensional being would have a desktop in front of it that's 3-dimensional, right? Because it's 1 dimension less. And so it would look down onto its 3-dimensional desktop, and it would see the world we live in, right? The 3-dimensional world. So when we plot a point in our 3-dimensional space, this being sees it in its 3-dimensional desktop. So it could then take these points and pull them up into the 4th dimension, right? And so what's happening here is, it's very foreign in some sense because we can't think in 4 dimensions, but at least you can see that there's a pattern here, right? This is just the continuation and extension of a pattern that started when we went from 2 dimensions to 3 dimensions. And of course, once, if you believe me at this point, if you don't, then we're in trouble. But if you believe me at this point, then of course there's no reason not to go to the 5th dimension, right? And then 6th, and so on. 10 dimensions, 100 dimensions, 1,000 dimensions. So now we have to be careful. So that you guys have probably heard the curse of dimensionality. So a lot of our intuition about geometry breaks down when you get into really high dimensions. And I'm going to not talk about that too much in this talk. I mean, so you have to be careful. So there are warning signs everywhere when you do this, but in general, you can sort of translate your intuition about lower dimensional spaces into these higher dimensional spaces. And then when you actually start doing this, you have to sort of start reading the warning signs. But we won't read the warning signs in this talk. But just they are there. Okay, so we now have these higher dimensional spaces that we're willing to work in. So great. So if someone gives you data that's just a string of numbers with lots of numbers in it, we now know how to handle that more or less. At least we know how to think about it, right? It's geometry. But of course, again, the data that we're interested in usually doesn't come in that form. So right, this is the age of the information age, right? So we've got what's important. We've got text, right? We've got Twitter. We have images, videos, sound. So we really want to be able to handle data like that. And it turns out that you can even extend this framework, this idea of geometry, to these other types of data. Oh, sorry. Before we do that, just as a historical note, this is the famous iris data set. So this is 4 dimensions. So each color is a species of iris. And this is 4-dimensional data that's been projected down to 2 dimensions, and you can actually see that each dimension, each species kind of takes up its own kind of geometric, makes its own geometric shape in 2 dimensions. It's even more so if you can actually see it in 4 dimensions. So anyway, so we see that. I guess this is meant to illustrate 2 things. One is that you actually do get geometric structure, right? You can sort of see the shapes that correspond to a real-world phenomenon, the species. And then the other one is this was 1936, right? So this is still kind of old style data analysis, right? So what we're interested in today is things like words, or sorry, let's start with categories, right? So you're an e-retailer and you want to understand what your customers are buying. So here are 3 of your customers, and here are 4 categories of the things that you sell. So Andy has bought books and electronics, and Betty has bought electronics and clothes, and so on, right? And so these are so this is data, right? So okay, so we're still in the realm of numbers here, But this is so we're taking categories and making numbers, and maybe that doesn't mean much. But so let me show you quickly. So now we're taking this list of numbers, and we're now kind of thinking about it geometrically, right? So now each of our users or each of our customers isn't just a row of numbers; they're actually a point in the space. And of course, there may be some overlap, but now we have points in a geometric space, and so we can apply these same algorithms that work geometrically to this problem. Okay, so that's we're stepping a little bit out of the 1936 world, out of the realm of numbers. So we can do something very similar with words. So if you're looking at tweets, or if you're looking at books, things like that, news articles, what you can do is you can take each block of text, and you just look at what words are in it, right? So you see, again, you put a 1 if that word is in that block of text, and a 0 if it's not. Okay. So this is called the bag of words vectors. And so now, again, our tweets or our sentences, I guess these are pages out of a children's book, right? They now sit in this geometric space. So again, we can use geometric ideas. The same algorithms that we could have used for our numerical data now allow us to analyze sentences or fragments of text or even larger chunks of text. The problem, of course, is that this doesn't tell you about word order, right? And so that's gonna so if you rearrange the words in a sentence, you're going to get the same bag of words. So there are various tricks for dealing with this. So one is what's called Engrams, where instead of just looking at single words, you look at pairs of words that come one after the other. So here are a couple. Oh, and in all of these slides, by the way, I'm showing you a few, but of course, in reality, we're doing this for all the words, or all the pairs of words, or all the triples of words. So we're getting thousands, maybe tens of thousands of dimensions, but we're still, modulo the recursive dimensionality, we can still think about this geometrically. So now, so now this gives us, so this is one of the tricks that you can use to kind of take into account word order. And so a lot of the modern natural language processing uses this sort of approach. And in fact, from what I understand, and I'm not an expert, but from what I understand, natural language processing is kind of in a shift from doing its own types of techniques that were sort of specialized to sentences, and it's kind of moving more towards standard data analysis techniques that kind of have this underlying geometric framework. Okay, so then there's a few others, so for example with sound, which is even harder. You can do something where, so these are supposed to be waveforms from sound. Of course, you can take waveforms from anything. So this is roughly this idea of wavelets, where you take a little snippet of sound and you basically go along the entire the entire time series, and you look at how closely it matches to any point in the time series. And if you see that little snippet somewhere, you put a 1. If you see it, if you don't see it, put a 0. If you see it and it's a little bit quieter, so like in the third one, you can see that it's got that first, the two, the up and the down waveform, but it's a little bit smaller, so you put a half there. And this thing on the left is supposed to be what you would get if you superimposed these two. I don't know if it actually is, but we're going to pretend. So this is kind of so again, you can take something very complex like sound, and you can turn it into this geometric framework and use these same techniques. Okay, so then, of course, the real interesting one these days is pictures, right? So these are 8x8 images that came from scanning. They had a bunch of people, I don't remember the exact number, just write the digits from 0 to 9, and they scanned it all and put it into these images. And so there, you have a few thousand of these. So each of these is 8x8, so it's a 64-bit image. It's so that's actually not too bad, right? So each of these is defined by 64 pixels, each of which is a value from 0 to 255. And so you actually have this is already more or less in the form of a vector, but it doesn't feel like a vector even though it is. So the question then is, does does this geometric perspective actually help us understand pictures, or is it going to just give us garbage? So I want to prove to you that at least in this case, it does. So here is an algorithm. This is a picture of an algorithm called Kmeans. And the idea behind Kmeans is, so this is often used as a clustering algorithm, though I'm using it in sort of a different method here. So what we do is we start off with these blue points, which are randomly distributed around our two-dimensional plane, and of course, in reality, we're doing this in the 64-dimensional space of the images. And we calculate what are called the Voronoi cells, which is basically just a cell. So it's all the points that are closest to any particular of the blue points than they are to any other ones, right? So this is sort of the points that are so this cell in the bottom middle. Those are all the points that are closest to that bottom center blue point than they are to any of the other points. So then what you do is you take each of these points. So these are the red ones in this picture. Are what we get if we take all of our data points in that cell and just move our initial point to the center of those data points. So the idea is we're trying to distribute our blue points in such a way that they're as far apart from each other as possible, but as close to the data points as possible. So you do this over and over again. So you calculate your cells where all the points that are closer. So basically, you take all the data points that are closer to any one of these cells than to the other, any one of the blue points than to the other ones. Then you move the blue point to the center of all those, and then you repeat this a few times. And what you get is something like on the right, where the blue points are now, instead of being just kind of haphazardly spread around the plane, they're now spread around the sort of shape that we would see if we actually, if we knew what the probability distribution was. They're kind of they're sort of now nicely distributed just within that shape. Okay, so again, this is a geometric description, no equations. I guess I sort of described it as an algorithm, but we don't, no code involved. So it's all geometric. So the question is, what happens if we take our initial set of pictures of numbers and do this, right? So maybe we get. So by the way, if you randomly took a bunch of numbers and you took, say, the average of them, right? The sort of the vector that's sort of in the center of all of those, you just get a gray blob. It's sort of darker in the middle and lighter on the outside, but it's just a gray blob. So there's a reasonable chance if we do this that we're going to get a gray blob. But it turns out that we don't. And so we actually get, so this is with I think there were 50 images. We could have done, you could do it with just 10, trying to get one representative of each number, but of course there are different ways of drawing numbers. And so what we see is that you actually, most of these are kind of discernible as numbers, right? So, and notice that none of these, no picture here was actually one of the images that we scanned, or that someone else scanned from a handwritten digit, right? So these are all artificial numbers. Each of these is the average of a bunch of other numbers, most of which were probably pretty similar to the one you see. So these are the images that represent those points distributed around this 64-dimensional space. Okay, so in this case, at least, the geometry actually works, right? This geometric, this sort of intuitive geometric approach actually gives us real data. And then, so this is of course, this works well if your topology is of the same size. There's some other tricks like convolutional neural networks. I don't know if you guys have heard that term. That got a lot of press a few months ago. Those use the same idea, but it basically combine this with more or less this idea, where instead of just looking at comparing a single set of pictures, you sort of you take one picture and you kind of move it around a larger picture and try to see where it matches up the best. Anyway, so the point is, it's all geometry. Okay, so I think I have enough time to go into the more cutting edge stuff. So this is my sort of spiel for why geometry is important to data analysis in general, in particular for understanding these basic techniques, right? So the idea is nowadays the tools are getting so good, right, that you don't actually need to, you can use the tools without knowing what the equations are. But if you don't understand what the tools are doing, you can get yourself into a lot of trouble. So the idea is And if you sort of have an intuitive geometric picture, you can use those tools without having to go into the technical details, and also sort of figuring out where you might go wrong, or at least figuring out why things went wrong when they did. So that's the first half. Okay, so the general kind of problem that still arises with most of these basic techniques is that they're very good at picking out simple structures, right? So like regression, if your data is falls along a line and you run regression on it, then it will tell you what that line is. If your data is not a line, right, like the picture on the right, then and you run regression, it's still going to tell you what that line is, but that line is going to be meaningless. And so where things are headed is kind of coming up with algorithms that will give you a better understanding of what your structure is. So remember, so in this picture we can see that the data on the right doesn't form a line. But of course, if we're working in a 1,000-dimensional data set, or even in a 4-dimensional data set, it's going to be much harder to see that. And there are visualization techniques that can help, but the visualization techniques will almost always distort the data. So what we really want is tools that will allow us to we'll kind of pull out nice information from these higher dimensional data sets that we can't see. And so I'm going to go into some abstract mathematics here. So topology, which is what I studied when I was an academic. And so the idea is, and this idea goes back to kind of the late 1800s, maybe even the mid 1800s. So when we talk about geometry, we talk about rigid shapes, right? Two shapes are geometrically the same if you can pick one up, so being like made of metal or hard plastic or something, you can pick it up and put it down on top of the other shape, it's the same. So the idea of topology is that when you get into more complex shapes, especially higher dimensional shapes, there are other things that are more important than these rigid properties. So in particular, right, so if you were to say geometrically, right, the top two pictures look very similar and the bottom two look very similar. So topology says, well, what if instead of being made of rigid metal and plastic, what if rubber? So the idea is you could take this coffee mug on the left, and you could kind of pull, you sort of flatten it down, and then sort of squish it into a ball without having to break anything, without having to rip it, and without having to kind of, you can do all that without having to actually glue anything together. Or maybe it's better to think about it in terms of the ball. If you kind of make an indentation on top of the ball, this is sort of the way you make you're making something out of clay. This is the way you might make that mug, right? You can sort of make an indentation and turn it into the mug. But right, because there's this hole right there. So from a topological perspective, the donut on the right has more in common with the mug that has a handle than with the ball, and the two mugs. So the mug on the left has more in common with the ball than it has with the mug on the right, because we have that hole there. So this is this. I know this probably seems kind of silly. What does this have to do with data, right? So the idea is that we're looking here for different types of structure in geometric objects, right? We're kind of instead of focusing on the rigid properties, we're focusing on these properties that don't necessarily have much to do with the rigid structure, but have some kind of deeper fundamental structure. And so in data analysis, when you get into these more complex data sets, you kind of want to do the same thing, right? So we want to look for structures that aren't necessarily geometric, right? So for example, if we had this loop of points, right, and if there actually was that hole in it, that would be really interesting from a data analysis perspective. But if we use something like like linear regression, of course, it wouldn't tell us that. So we don't necessarily want to look for holes. I think holes like that happen fairly rarely in practice. But although it's unfair how often they happen. But we kind of want to look for structures that are more complex than what we usually look for in basic statistics and machine learning techniques, right? So maybe something in the middle, like looking. So this is like looking for clusters, where we have something it's not just a property of the rigid data set, right? If we were to sort of move the points around a little bit, that the fact that they made this dumbbell shape wouldn't change. So what we want is something that sort of is in between this kind of very abstract topological picture and the more traditional purely geometric picture. So I'm going to let's see. So I'm going to talk about for the rest, for maybe 10 more minutes, is something that is on the far right of the board. So we're going to talk about pure topology here, and I'm not claiming that this is that these are techniques that necessarily have killer applications, but I think this is something that has some ideas that could be very helpful to the field, and that could lead to some very interesting techniques. Now they're all going to be computationally infeasible for large data sets, warning you now. So, but I think there's some interesting ideas there. So the basically when we start getting into these more complex structures, suddenly this idea of what should the probability distribution look like is much more important, right? When we had that, when we were doing regression, we knew roughly what the distribution looked like, right? It was the concentrated along the line and then getting less concentrated as you move away, and it was just a matter of kind of moving it around to fit the data set. But now, if we can pick any distribution, suddenly it's not a matter of kind of fitting it to the data set. We actually have to make some real decisions. Is this set of points? Is it a loop? Is it 2 blobs? Is it 6 blobs? Right. So we have a lot more possibilities, and it gets it's enough rope to hang yourself. So one idea which this topological approach, or the mathematicians who are working on, we're coming from the background of topology, have adopted this idea of epsilon balls. So in topology, anything that is so a disk is a 2-dimensional ball, and then there's 3-dimensional balls, 4-dimensional balls, and so on. So anyways, so the idea is you take all the points that are within some value of epsilon. I'm sorry if you're afraid of Greek letters, which I don't blame you. You can pretend that's something else. Anyways, it's just some distance. So we take all the points that are within that distance of the point, and so what we see is that points that are close to each other. So this is supposed to be the distribution made up of all those points. So we kind of get these blobs, and so this gives us a way of sort of saying what that distribution should be in a fairly straightforward way. And of course, we still have this problem that we have to decide what epsilon is. It's a Greek letter, but we still have to decide what value it takes. And so you can see, right, like we here, if we pick it too small, we get 2, or if we pick it on the smaller side, we get 2 blobs. If we pick it bigger, we get 1 blob, right? So we still have this choice. This hasn't actually solved the problem. But then, and if there are any computer scientists or anyone who works on large-scale data, I apologize for the next slide. So what we're going to have to do is look at, in some sense, look at all possible epsilon, right? So the reason I'm apologizing is because this is, of course, computationally expensive, because now you've taken whatever, if you have whatever your computational complexity was, you just multiply it by n, for some reasonable n. And but now what we can do, if we're willing to do this, is we can look at how the structure changes, right? So we start off with 6 points, and then when epsilon gets to a certain stage, we switch to just 2, and then when we get later on, we get back to 1. And so if we were to look at this, and if there was a sort of large gap where it was exactly 2 blobs, then we would say, okay, well that must be significant, right? Because it's 2 blobs over a large stretch of scales, right? So you can imagine kind of zooming out and zooming in, and if you sort of slowly zoomed, I guess if you slowly zoomed out, there would be a long period where it looked like 2 blobs, so that's probably significant. So this is actually fair, not that new of an idea. So this is sometimes called the dendrogram. The idea is you start off on the left with all of your points, and then whenever 2 of these balls overlap and give you, they sort of merge, you just draw. So this is called a tree. You just kind of connect those points to each other, and so now this dendrogram that we get, you see that there's this long gap where there are exactly 2 branches. And so this is sort of encoding the structure. And so if you saw this, you would say, okay, so this should have 2 blobs. So now what we want to do is the same thing, but for more complex structures. So again, we're talking about topology, so loops or holes, however you want to think about it. So in topology, there are these things called homology groups that allow you to count how many holes a geometric object has. Now, counting holes in a geometric object in a shape is really easy, right? If it's a two-dimensional shape, that's not even high school level geometry. But doing it in higher dimensions is of course, more difficult. And so this is basically so homology groups you can think of basically they're a way of talking about an algorithm that will find the number of holes. And so if you apply this theory to this data set, what you'll find is that initially there are 0 loops. Right on the left, there's no loops. In the middle, there's 1 loop, right? And then at the end, there are 0 loops. Right? Is that okay? So here, what you would get is that that there's a large span from going from where you have exactly 1 loop, right? Since early on you go to 1, and then it's only at the end that it sort of gets filled in and you go back to 0. So the idea of persistent homology, and I think I forgot to actually write the word persistent homology here. So this is one of the ideas that got me interested in data analysis when I was started out as a pure mathematician. Was this idea of persistent homology? So taking this theory that goes back to the mid to late 1800s and using it to understand these data sets. So here we have a slightly more complex circle. So we have so at some point the output of persistent homology is what's called a barcode. So here when we get to a certain point, these balls merge together to form a loop. So that's when we start this lower barcode. And then when it gets a little bigger, you can see the loop actually merges with itself in the middle. And so now we have these 2 loops. I think you guys can see that white triangle up there, right? So there's actually 2 holes in this object now, which is kind of strange because we didn't actually poke a hole in it. We just merged it, which created a hole. And then you go a little farther, and that top hole gets plugged, right? Because the balls are getting bigger. And so then so the barcode corresponding to that top hole goes away, and then a little while later, that the one remaining hole gets plugged, and so this bar goes away. And there's some very interesting but kind of esoteric mathematics that will tell you exactly how to create this barcode. But the point is that this is one way, again, very computationally expensive, but this is a way to get some information about the structure of this data set that you wouldn't have gotten from traditional techniques. And so this barcode, of course, is something very simple you can look at and you can interpret it. If there's a long bar and then some other short bars, that one long bar means that your data found probably has a loop. If there's 2 bars and probably 2 loops, things like that. So anyway, so this is kind of some more geometrically, topologically inspired work on data analysis. And so I think probably these algorithms as is are not going to scale low enough, but I think there's some really interesting ideas in here that once they make it into the more mainstream data analysis community, I think could be really powerful. So, anyways, I'm going to end there. Thanks.
Could you comment, because going back to the previous figure, so many times when you run k-nearest neighbor algorithms, which should be roughly sort of identical to sort of creating these balls around things, many times when you run them, you actually get a fairly flat learning curve as a function of k.
Oh, as a function.
As a function of k.
So what do you mean by a learning curve? You mean?
I mean, I don't mean as a function of data, but I mean as a function of complexity, right? I mean, typically you're looking at your test set and you're looking at a complexity which bottoms up.
Oh, I see. You're saying the computational complexity is sort of...
No, not the computational complexity, but the complexity of the model. Like, is it really small k, right, in which you're in the variance limit, or large k when you're in the bias limit?
Oh, I see.
But you're in between somewhere where you're sort of like balanced between the two. And typically you actually, I mean, practically find that a lot of these data sets have fairly flat curves.
I see. So you're saying that there's a sort of range of values of k where the measures of how good the model are very similar.
Right, and so there ought to be somewhat of a similar, I mean, intuitively, there ought to be somewhat of a similar sort of like range of if you like, holes.
Yeah. So somehow the k there, it may be doing a similar thing of sort of defining a scale on which you're sort of learning the data set. Yeah, I think that's nice. I didn't know that, but that's a good point. So it probably is the same idea. And then again, you can think of this as sort of trying to find the right scale to analyze the data on in a lot of ways. And so yes.
But is there any research on like what the homology number is with respect to K or anything of that sort on these data sets? Because you could actually solve these problems by just making epsilon balls instead of doing K nearest neighbors. There should be some correspondence between the two.
Oh, I see. Yeah, that's a good question. I don't know offhand of any research that's looked at K nearest neighbors, but or compared to this, yeah.
I think this is probably more analogous to mean shift clustering. Have you heard of
Mean shift clustering? No, I haven't.
So it's basically this epsilon balls concept. Instead of having a rigid ball around every data point, you sort of tack a Gaussian blob on top of every data point.
Okay.
And you look at how those Gaussian blobs sort of coalesce and make structures, and then you look for places where, the overall landscape sort of makes a big mountain, and you say, okay, well that's a cluster versus big mountain.
Okay. Yeah, so I hadn't heard of mean shift clustering before. That sounds interesting. So certainly, I mean, in practice, these ought to be Gaussian balls. It's just that when you're doing these sorts of calculations, it's a little, since we're talking about topology here, to say what it means to have a loop, you kind of need to have need to know what's in the set and what's not, But yeah, I think that sounds like a very similar concept. Okay, I think
One of your earlier slides, it looked like certain data points could be much more critical than others. Like in an early slide, you had for classification, like 3 regions, 2 of which were connected by an isthmus.
right. Yeah. So
Yeah, go for it.
you mean
There.
this one or the
One,
I see.
there. So you have
Yeah.
3 regions, 2 of which are connected by an isthmus. And if you cluster those, you get what you show on the slides. But if only 3 or 4 of those data points change so that the isthmus connects the other 2 regions, the whole clustering changes just off of very few data points changing.
Yeah. So depending on how you're doing the clustering, right, a couple of changes to the data could, or a couple of small changes could impact this. So and depending on the clustering algorithm that you used, it may not matter if there was a bridge between those two. So for example, there are some clustering algorithms that would that would recognize. So for example, the two green blobs, right? If we were to depending on the algorithm, if you were to tell it there are 3 blobs instead of 2, it would it could potentially find that that bridge there. And so it might not care if you added a few blobs between the green and the blue as well. But yeah, I mean, that's a good point. I mean, and of course, in higher dimensions, it's even harder to tell what these sort of small perturbations. I've lost track of whether they're hand up first. Go ahead.
This epsilon balls algorithm, how is it dependent on scaling along different dimensions? Because it assumes that the scale is predetermined, but sometimes it's not really.
Yeah. So remember, this is sort of this is developed by mathematicians as opposed to data scientists. So the theory tends to kind of gloss over a lot of those issues. So but absolutely. So how you scale individual dimensions will have a big impact. So I think usually the sort of the setting in which this is talked about is that you've somehow figured out what the right scaling factors are, and then you apply this analysis.
But you didn't experiment with the changing scales and see how things change, how it behaves?
That's a good question. So I'm sure people have. That depends a lot on the data set itself, right? So I don't know offhand of any research looking at scaling individual dimensions, but it would surprise me.
Should be taking care of that metric.
Well, right. So the question is, what metric do you pick?
Right, if you use a consistent metric with inconsistent scale, then it doesn't make sense. But
Right.
if your metric is consistent with the scale.
Yeah. So if you're right. So if you have a data set where the different dimensions are all kind of coming from the same type of data, then of course you can but if you have different types of signals making it the different dimensions, then that's going to be a big factor. Yeah. So and again, this is one of these things where this is still very very abstract. Yes, go ahead.
Give me an example of two types of texts which are topologically different.
Sorry, say it again.
I mean, your suggestion is that you can analyze complex data, text, for example. Text are, let's say, higher dimensions of data. Did you try to see, I mean, at least do you have an example of two types of texts which topologically differ?
Text which is topologically different.
That would be well eliminated. Like, let's say you say, okay, legal documents, okay, they go to that part. And for example, let's say geographical, okay, national geographic is that.
Yeah, so it's very hard to, there aren't many examples of data sets where you actually see these loops. So usually they're fairly specialized. So things like, there's one example that was kind of nice where they were, the data was basically clustered into 4 different communities, and there was sort of a loop that you could pick out between the 4 of them. There was sort of, the way that they sort of overlapped gave you a loop. So there are things. So most of the examples where you actually can see a loop are sort of specialized like that. So I think
Nothing I can relate to. Nothing practical.
Yeah, so that's why. So I tried to include that caveat as much as possible. Yeah, so this is still very much fairly abstract ideas, looking for good applications. And I think the importance of this isn't so much in the algorithm as it exists today, but as sort of what ideas you can take from this and apply to.
But is it possible that topology is a better tool for investigation?
I mean, it's possible.
Then geometry is even topology.
Yeah, so I think that there's an element of topology to many of these problems, in the sense that often you'll find yourself looking for structure that holds up under these small perturbations, right? Which is essentially what topology is. So like the clustering, for example, I think is a fairly topological problem, in the sense that the fact that so if you were to look at the two regions here with a small bridge between them, if you were to move them around, we don't care. So the fact that there's two blobs with a bridge between them doesn't matter exactly how they're configured. It doesn't matter geometrically. It's really something that sort of that holds up under at least moderate deformation. Does that make sense? Yeah. So I don't have a killer app to convince you that they're
Well, topologically, for example, is 5 people versus one, right?
Which is what?
People topologically are different from one, right?
People versus yeah.
Let's say you have a totally blind person, right? And he just gets data density. You can say, okay, these structures that correspond to people, and these are the ones, right?
Right.
So there's a code that, let's say, with text. Maybe you'll discover there are texts which are like people. Only 3 types, right? Or 4 types, right?
Sure. Yeah. So I mean, I think it's going to be really exciting to see what can be done. But I don't have anything for you today. Yes.
Hey Jesse, do you mind repeating the question?
Oh yeah. So the question.
The next question.
The next question. Okay.
That's what you know your answer. Thank you.
Yeah.
So one of the problems you mentioned was the whole concept of scaling. When you get a lot of data, and now suddenly you're multiplying by n because the number of epsilons. Have you done any research into if you use, say, a consensus algorithm like ransack, if we just chop down the number of points we use to fit the models, is that going to be still feasible, or are things going to break down?
Oh yes. So in fact, so the question was if since doing this on large scale data sets is often computationally feasible, are there ways to sample essentially the data in order to get a smaller data set that you can use this on? Is that
Yeah, we can use ransack or something like it to form over a bunch of hypotheses and see which one provides the best support or best fit.
Yeah. So in fact, often in practice, at least in a lot of the earlier work, they would sample. They basically would take the densest part of the data set, and so because the shapes are often they're sort of fuzzy. kind of Gaussian looking. It's if you take all the data, you'll often have the holes will be filled in right away because you'll have a few data points in all those regions. So it's common practice to restrict yourself to the data points that are denser or that have a lot of neighbors, and so that goes a fairly long way towards reducing the size of the data set. I don't know if how much work has been done on sampling beyond that, but I think certainly if there's topological structure there, it should it should remain after if you've done some reasonable sampling.
Take one more question, Justin, if you don't mind.
Sure. I think in the back
You mentioned the ideal wavelength, so we are on the part. Do you think you could combine the wavelength regular representation with topological concepts in terms of instead of using just a single circle, using a library or a set of geometrical or original like so-called other functions or some sort of modulations?
I see. So the question is whether you can combine the idea of the wavelet where you're looking at a small portion of the data with the topological idea. I think I think you probably could. That is, do some kind of local analysis where you say take all the data points within some fixed distance of a point and see if there's topological structure there. Is that?
Yes, but it could be extended, not necessarily just local, it could be extended over the playing by shifts, like in regular sense.
Oh, I see.
Dilations and modulations.
I see. So you're talking about shifts and dilations of the circle. So well, the interesting thing about this being a topological approach is that it doesn't actually, it's not looking for a specific circle. It's looking for a loop. That is, so particular, the loops that it finds here, they're not round circles, right? They're just some kind of, So in theory, at least, this takes away the need for something like that. Is it one more?
One more. It's up to you.
Okay. All right. Go ahead.
Quick question. So this is a really interesting talk. For the talk even about an esoteric application, just anything you've seen it used for, I'd love to just hear more about that, even if it's very sort of contrived.
So let's see. So I mentioned there was there's one application with there was I think this was a group of people that had formed 4 communities where sort of the two are very close to each other and then the next 2 are very close, and so you could sort of see, like if you looked at the data in the right projection, it basically looked like 4 blobs, kind of the corners of a square, and so the analysis showed the loop that you get by sort of going around the 4 of them. There was the original data set that sort of was the original application was basically taking, I think it was 3 by 3 squares from random pictures and sort of adjusting them in the right way, and then just taking this sort of data set of all really tiny sort of snippets of pictures. And what they found basically was that you tended these pictures that you got when they were just correctly tended to look like basically lines that were centered at the middle. And so what they got was basically this loop that you get by sort of following different angles. So they were actually able to see this sort of loop of angles in this set of pictures. Is that, the question was at least mention a couple of examples where this actually finds structure.
All
right, go ahead.
So is there a relationship between the homology group of a particular data set and whether you use a kernel to transform it? Like you would think that if you have a data set which is in 2 concentric circles, and you have a homology group of 1 because you have to draw a circle in between it and you're actually enclosing something, and if you actually expand it by putting it on a parabola or something of that sort, and you get very clean linear separability, the homology in this expanded space goes down to 0. So it doesn't seem to be an invariant quantity on a kernel transformation. Am I wrong, or?
Right. So the question you asked if
is the homology of the data set as a way of the picking of the holes, if you like, is it invariant to a kernel transformation to a higher dimensional space?
So is it invariant to a kernel transformation? So my guess is that in most cases it would be, just because when you do a kernel transformation, you're not you're basically you're deforming the data, but you're keeping, generally you keep nearby points nearby, right? So I mean, as long as the kernel transformation wasn't too extreme, where you were actually sort of stretching the points to where this would no longer.
Take a simple example of putting things on a paraboloid. So if I have two concentric circles, the first thing goes at the bottom of the paraboloid, and the second thing goes up on the paraboloid. So you're going from a two-dimensional space to a three-dimensional space.
Sure.
And there is no homology left in the three-dimensional space because I can just get these things.
Or
am I just completely not understanding this? Which is quite likely.
Yeah. The question was, so I've given you a very vague definition of what a hole is. Or what a loop is. So the question was, if you take a two-dimensional, say two concentric circles, and you transform it into three-dimensional space in a way that sort of lifts one circle above the other, does this homology still work? And the answer is yes, because what it's looking for is basically that you can sort of follow a path around the data points, and get back to where you started, but then you can't sort of shrink that path down while keeping it near the data points. Yeah, so that's closer to the technical definition of homology that I've been avoiding.
So everyone, thank Jesse. Great talk, as always, and great Q&A discussion. I'm sure Jesse's going to hang around because I'm sure there's going to be a few more questions. And see you guys next month. Thank you very much for coming.